This is the supplementary video for the paper Flow Shadowing, a method to detect flow headings using an array of densely packed Whisker-Inspired sensors. The goal of this research is to develop a sensor that can go on a drone and understand multiple flows coming from multiple directions at the same time. This is challenging because multiple flows often will be read by flow sensors as a combined signal, but what we want to know is distinct information about each flow. We accomplish our research goal by combining 4 of the Kim et al. Flow sensors into a 2x2 array. The sensor works as a drag element rotating in the wind, and a magnet Hall effect pair allow us to sense the rotation. The array is important because it allows us to take advantage of a phenomenon that we are calling flow shadowing. In flow shadowing, there is an upstream and a downstream whisker. The downstream whisker is in the upstream whisker's shadow, and therefore does not receive as much flow as the upstream whisker does. We can see this as well in the signal response. This leads to a direction-dependent asymmetric response across the upstream and downstream whiskers. When multiple flows are introduced, the flow shadowing becomes multidirectional. In this example here, we first introduce flow from a single direction, phi 1 equals 0, and it most affects whiskers 1 and 4. But then we introduce a second flow at 90 degrees, which affects whiskers 4 and 3. You'll notice whisker 3 and whisker 1 are responding each to the flow that they are not blocked from, much more than they are responding to the flow for which shadowing is occurring. This is helpful later when we want to develop an algorithm to understand these flows. In the examples we've shown thus far, the videos have been at 100% occlusion, which means that the whiskers were directly upstream downstream from each other. But this isn't true in all cases, so we performed experimental tests to measure how different occlusions affected the amount of sensor signal we received for each whisker. Using these experimental results, we were able to model how the flow would change if it were coming into different directions on the 2x2 array. This is the animation that you see on the right. As the flow direction changes, the amount of occlusion changes, which changes the strength of the sensor signal. The sensors closer to the flow always have the strongest signal. We use the known expected response of the array in our algorithms. In the first algorithm, we assume that we know the heading of one of the flows. So we subtract how that heading would affect the array in order to figure out the heading of the second flow source. In the second algorithm, we predict no prior knowledge of the headings of the flow. To predict heading 1, we pick the sensor direction signal that is farthest from the average direction signal. We then use this prediction in order to solve for the second heading, using methods similar to algorithm 1.